The derivative function. So up until this point in the course, we've been laying the foundation so we could finally reach the point where we talk about the derivative function. So again, the derivative is going to be the function that will allow us to get the instantaneous rate of change at any point for a given function. This is really powerful because again, if we know how a function is changing at a point, we know a bit about what the function's doing, how it's behaving, how we think it'll behave in the future, and we can use it to predict future values. Now, there's a couple ways to study the derivative function. The first is the algebraic and mathematical definition of derivatives. Before we get into that, I want to remind you that when we talked about continuity, we talked about how polynomials are continuous wherever they are defined. And we talked about what that meant. It meant that the limit was equal to the functional value. That's how we defined continuity. So that's really helpful for us because that means if we're taking limits and we're looking at a polynomial term, so polynomials are things like x squared, x cubed, or whatever variable you're going to be using, that if the function itself is continuous, then we can plug the value in. Because it's continuous, it will be equal to the limit so that we don't have to do all the tedious calculations of small numbers. So let's start with the algebraic definition of the derivative function. So the definition of derivative says that for any function f, we define the derivative function f prime of x by the limit as h goes to 0 of f of x plus h minus f of x over h. Provided that the limit exists, the function is said to be differentiable at any point x at which the derivative function is defined. So that means if we have a function and we want to get the derivative function, which again will be the function that'll tell us the instantaneous rate of change at any point, we can use this limit to calculate it. I hope that the top of this limit looks familiar. If you think back to our composite functions, we were doing a lot of things like f of x plus h within our composite function section, which we'll now be able to apply here. Why does this definition make sense? Let's take a quick sidebar and look at a picture so we can understand why this limit will give us the definition of derivative. So remember, to get the derivative, we were using what we knew about the average rate of change to help us find the instantaneous rate of change. So we began by calculating f of b minus f of a over b minus a. Now, a and b were generic things that we chose to represent the endpoints. We don't have to use a and b. We could use c and d. We could have used f and z, right? These are just letters to represent two endpoints. So we could call one of them x and the other one x plus h. So what it is it's the x value plus some amount, meaning that it's to the right. Now, if we were to set up the average rate of change using x and x plus h, we would have f of x plus h minus f of x all divided by x plus h minus x, right? So f of b minus f of a over b minus a. Notice what happens on the bottom. We have an x and we have a minus x. So that simplifies into f of x plus h minus f of x divided by h. So the average rate of change between these 2 points is f of x plus h minus f of x all divided by h. That's equivalent to f of b minus f of a over b minus a. Where the limit comes in is this idea that the closer we get to the point we're interested in, right? We want to get smaller and smaller intervals by moving this point closer and closer. Now, before, we were just picking brand new values, but the equivalent statement here is letting h get really, really small. Because if h gets really small, that means that this point is moving closer to the point where we're trying to approximate. And the way we represent something getting really small is by introducing a limit. So we say the limit as h goes to 0, so that means that our average rates of change are getting closer and closer to x, gives us the derivative at that point, or the instantaneous rate of change. So let's start with an example and see how we can use this definition to find the derivative function. Example 1. Use the definition of derivative to find f prime of x if f of x equals x squared. So again, we're thinking about the function x squared, and we're trying to find a function that will tell us how quickly x squared is changing at any given point. So we go to our limit. So the definition says we're going to take the limit as h goes to 0 of f of x plus h. Now, let's do that as sort of a sidebar here so you can remember how we do that. F of x plus h means we're going to plug x plus h into our function. And our function was x squared, so that means f of x plus h is x plus h squared. Now here, we plug that in, we have x plus h squared minus f of x, so our f of x was x squared, all divided by h. Now, we want to start to do some of our algebraic simplification here. So what we're going to do is we're going to square out that top term to see if we can combine any like terms. So we get the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared, all divided by h. So here we have an x squared and we have a minus x squared. So those two terms will cancel, which leaves us with 2xh plus h squared divided by h. We can factor out an h term in the top here. So we have h times 2x plus h, all divided by h. Our h's will cancel, and we're left with the limit as h goes to 0 of 2x plus h. Now think about what kind of function h would be. If we just have h, that means it's a polynomial. It's raised to the first power. Since it's a polynomial, that means the limit as h goes to 0 is the same as if we were to plug in 0, because h itself is continuous. We couldn't do that before because it was in the denominator and it wouldn't be defined there. However, here it is. So we can let h go to 0, which means we're left with a 2x. That means that the derivative of this function is going to be 2x. So again, the derivative is a function. And what that function tells us is the instantaneous rate of change of x squared at any point. So if we want to know how quickly x squared is changing at 4, we could plug that into our derivative function and we would get 8. So the instantaneous rate of change of x squared at 4 would be 8. And we can plug that into the derivative instead of doing average rates of change around 4. So instead of using 3.99, 4, 4.01. So this is a more effective way to do it if we're able to solve it out. So let's take a look at another example of finding the derivative using the definition of derivative. Example 2. Use the definition of derivative to find f prime of 0 if f of x equals 2x squared minus 3x. So before, when we were approximating the instantaneous rate of change at 0, we would look a little bit to the left of 0 and take the average rate of change, and a little bit to the right of 0 to get the average rate of change to try to see what it was approaching. But now we want to use the definition of derivative. So remember, the definition of derivative looks like this. So when we plug in this definition into our function, the first term is f of x plus h. So f of x plus h is this first part right here. We're going to plug in an x plus h wherever we see an x, which is here and here. So we have two different terms. And then we have minus f of x. So we write minus, and then we put our parentheses around the function because that minus term has to go to both terms of f of x, all divided by h. Now we need to start our algebraic simplification. So for the first step, I'm going to square out the x plus h in that first term. So if I square that out, I'm going to get x squared plus 2xh plus h squared. Remember, there's still the 2 out front. I haven't touched any of the other terms yet. Now, what we want to do is we want to distribute this 2 to every term, but we also want to distribute the 3 into the second set of parentheses. After distributing, we get this result down here. So the 2 went in to multiply every term in the first parenthesis, and the 3 went in to multiply every term in the second parenthesis. I want you to notice that the first parenthesis has a 2x squared, and the very last parenthesis had a minus 2x squared. So those two terms are going to cancel each other out. Similarly, we had a minus 3x from the first part of our term, and then we actually have a plus 3x over here. So notice that this was negative, but this minus is going to cancel it out. So these 3x's also cancel each other out. So now that those things are canceled, we're left with the limit as h goes to 0 of 4xh plus 2h squared minus 3h. So the minus 3h came from this little term over here that we've just been carrying along, all divided by h. So just like before, what I notice is that I can factor an h out of my numerator. And if I factor an h out, it's going to make my algebra a little bit easier. So here, when I factor the h out, I'm left with a 4x plus 2h minus 3. And I have an h on the top and an h on the bottom. So those will cancel. So now I have the limit as h goes to 0 of 4x plus 2h minus 3. So again, 2h is a polynomial term. And now that my h is no longer in the denominator, I can let h go to 0 because polynomials are continuous. And so after all my algebraic work is done, I have 4x minus 3. So remember what we were calculating. We were calculating the derivative, and we can write the derivative as f prime of x. So f prime of x equals 4x minus 3. But originally, the problem asked me for the derivative at 0. So since my derivative function will tell me the instantaneous rate of change at any point, I'm going to plug a 0 into my derivative, which will give me 4 times 0 minus 3, which gives me, ultimately, negative 3. So f prime of 0 equals negative 3. So that's how we can use the definition to find things algebraically. However, as your functions get more complicated, the algebra also gets more complicated. So we're going to take another approach at looking at the derivative function. We're going to do some graphical analysis to try to understand how to approximate the derivative from a graph. This is going to become very powerful for us as a tool to start talking more about the derivative function. Example 3. Estimate the derivative of the function at x equals -2, -1, 0, 1, and 2 for the function below. When we want to estimate the derivative of a function at a point, we're asking to approximate the slope of the tangent line at that point. So I've drawn in the 5 tangent lines that we're interested in trying to approximate the slopes of. Now, if I didn't have them already drawn in, I would take a ruler or a straight edge or use my best guess to try to visualize where that tangent line would be. So remember, tangent lines only touch at one point, and the point where they touch are the points we're interested in. So let's start by looking at the derivative of the function at -2. So at -2, My tangent line touches right here, and you can see it's sort of an orangish red color. So I'm trying to approximate the slope of that tangent line because it's the slope of the tangent line that will tell me what approximately the instantaneous rate of change is. In order to get the slope of a tangent line, I need 2 points on that line. If I have 2 points on the line, I can do the change in y over change in x to get the slope of that line. So remember, I'm no longer looking at points on the function when I'm approximating the derivative. I'm looking at the points on the tangent line. So I can pick any 2 points I want, but I'm going to try to pick them somewhat strategically. So here, this looks like -2, 4. And then down here, this bottom part of the tangent line looks like it goes through at -1, 0. Now again, I could pick any point on the tangent line. At the top of the line, it looks like -3, 8. I could pick something in between. I'm trying to pick numbers that are whole numbers to make my calculations a little bit straightforward. So again, I'm approximating the derivative at -2. And the derivative is the slope of the tangent line, which I'm going to calculate by doing change in y over change in x. So my change in y is going to be 4 minus 0. And then my change in x is going to be -2 minus -1. So on the top, I have 4. On the bottom, notice I have a minus a negative. So those are going to cancel, and I end up with -2 plus 1, which is -1. 4 divided by -1 is -4. So my approximation for the derivative at -2, which is the slope of the tangent line at -2, is -4. I'm expecting the slope to be negative because my tangent line is downward sloping. So this all seems to make sense with what I expected to happen. Let's go ahead and look at what happens at -1. At -1, my function is right about here. My tangent line touches. I've drawn in a blue tangent line to look at what's happening at -1. And again, I'm going to try to find 2 points that are on my line and use that to approximate the slope of the tangent line. So again, I'm going to try to pick these a little bit strategically. So this point right here where I actually touch the function looks like it's happening at -1, 1. So I go over -1, and then I'm about halfway between 0 and 2 on the y-axis. And then I have to pick another point that I think is on this line. So I'm looking over here, and this right here looks like it's at the point 0, -1. So both of these points are on my blue line. And again, I don't have to use these points. I can use any 2 points on that blue line, but these ones seemed like they'd be easy to work with. So now I'm going to do the change in y over the change in x. So the change in y, I'm going to do 1 minus -1. Right? So those are my y values. There's my 1. There's my -1. So the change in y, now the change in x is going to be -1 minus 0. So -1 minus 0. So on the top, the minus and the negative cancel, giving me 2. And on the bottom, I just have -1. 2 divided by -1 is -2. So the slope of my tangent line at -1, or the instantaneous rate of change at -1, is -2. So now, let's try the next one. The next one is at 0. So that's an interesting case here. I don't know if you can see, hopefully, that yellow line. But what's happening at 0, we have the point 0, 0. And then we also have pretty much any other point on the origin. So I'm going to use the same point over here, -1, 0, that I had used before. So if I do my change in y, I get 0 minus 0 over the change in x. So the change in x is going to be 0 minus -1, We have to be careful that we're not dividing by 0, but here we're not. We have 0 divided by 1, and 0 divided by 1 is 0. So if you have a fraction and you end up with 0 in the numerator, that means that the whole thing is 0. That's okay. We only have to be concerned if 0 is in the denominator. So that means the slope of my tangent line at 0 is 0. And that makes sense because if you can visualize that line, or if you can see it in that light yellow color, you can see that it's a horizontal line. And we know that horizontal lines have a slope of 0. So we'll continue working our way to the right. So the next point that we're interested in is going to be the point at positive 1. So at positive 1, we're touching right about here. And again, we want to find 2 points on this line. We can see that the point 0, negative 1 is on this line as well because they both cross through at the same point. And then we'll use the point 1, 1 because here when x was 1, it looks like y was also 1. So to approximate the derivative at 1, we're going to do the change in y. So we're going to do 1 minus negative 1 divided by the change in x, 1 minus 0. Again, if you subtract the negative, those cancel. So we end up with 2 divided by 1, which is positive 2. So we're expecting a positively sloped line because that blue line looks like it's going in the upward direction. So we were expecting a positive result. So that's good. And then finally, we want to approximate the derivative at 2. So at 2, we're right about here. We're picking 2 points on this line. So again, we'll pick 2, 4. That's 1 point. And then we'll go ahead up here and we'll pick 3, 8, which is sort of where I stopped drawing this line. But the tangent lines go on forever and ever. So again, you can pick any 2 points on the tangent line. Just choose ones that are easy to work with or the easiest for you to work with. So here, change in y over change in x. The change in y is 8 minus 4. And then the change in x is going to be 3 minus 2. So on the top we get 4, on the bottom we get 1. And so we get that the derivative at 2 has a slope of 4. So if we want to approximate the derivative at any point on a graph, we need to draw on the tangent line, find 2 points on that line, and approximate the slope by doing change in y over change in x. And that's how we approximate the derivative at various points on a function using a graph. Example 4. Find the intervals where the function below is increasing and decreasing. Determine if there is a relationship between where the function is increasing and decreasing and the sign of the first derivative. So our function is going to be increasing when the y values are going up from left to right. So the first interval where that's happening looks like it goes from -2 until 0. So we're going to be increasing from -2 until 0. And then it looks like again from 3 until about 6.25 approximately. Notice that 6.5 is here, so it's about halfway between 6 and 6.5. And then we're going to be decreasing when our y values are going in the downward direction. So that's going to happen from 0 until 3. And then again from 6.25 till about 8. It looks like the function is going to end around 8. So those are the intervals where we're increasing and decreasing. And the question wants us to look at whether or not that's related to the sign of the first derivative. So the sign means we're looking at things like positive, negative, and 0. So there's a difference between when things are increasing and decreasing and when they're positive and negative. So here in this original function, if we just look at the picture, this entire graph is positive because it's above the x-axis. However, there are places where it's increasing and places where it's decreasing. So positive and negative evaluates when we're above and below the x-axis, whereas increasing and decreasing describes what the function is doing as you move from left to right. However, we're trying to look at the sign of the first derivative, which means we need to start looking at some tangent lines. So let's look at the intervals where we're increasing. If we go ahead and draw in a bunch of tangent lines wherever we're increasing, we can look to see if there's any patterns here. So I'm just picking some places and I'm drawing them in. So when I look at these tangent lines and I'm trying to determine, do they have a positive slope, a negative slope, or a zero slope, I start to notice that all of these little tangent lines have a positive slope. And that's not a coincidence. Turns out, when your function is increasing, the first derivative is always going to be positive in those places. We can do something similar for our function here wherever we're decreasing. So if we draw in a bunch of tangent lines, wherever we're decreasing, which is over here and over here, what we're going to notice is that all of those tangent lines are negatively sloped. Negative, 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 negative. So that means that the first derivative is going to be negative whenever our function is decreasing. And what's also interesting to point out is that right where we turn around from increasing to decreasing, those are exactly the points where our slope is 0. So right at 0, right at x equals 3, and at x equals 6.25, the slopes of those tangent lines are going to be 0. And we said that those places where we change from increasing to decreasing or decreasing to increasing, we call those points constant. So when the function is constant, the derivative is 0. So again, if our function's increasing, any derivative that we calculate on that interval, we expect to be positive. If our function's decreasing, any derivative we calculate on that interval, we expect to be negative. And if we're at the point where we turn around from increasing to decreasing or decreasing to increasing, we're expecting our derivative to be 0. So this brings up our first set of rules about the relationship graphically between the original function and the first derivative. These are going to become really important, and we're going to build upon these as we look at different types of functions. So what we said is that if f of x is increasing on an interval, then f of x is positive on that interval. If f of x is decreasing on an interval, we say the derivative is negative on that interval. And if f of x is constant, then we say that f of x is 0 on that interval. This is one of the most important sets of rules that we are going to look at to begin building our foundation of how functions behave graphically. So it's really important that we start to practice this and have a really good solid understanding about this relationship before we bring in new relationships. So let's look at an example. Example 5. Given the graph of f of x below, determine the intervals where the first derivative is positive, negative, and 0. So thinking about our rules, if we want to first decide where the first derivative is positive, we want to find the intervals where the original function is increasing. So whenever we're increasing, the first derivative is positive. So taking a look at this graph, it looks like I'm increasing from roughly, so we're going to be increasing from negative, let's say 1.4 until 0. So this part of the line right here, right, we're going to be increasing all right here. And then again, over here, from about 1.4 till about 2.5. So if my function is increasing, then my first derivative is positive, right? So that means any tangent line that I draw where I have those squiggly lines for increasing. The tangent line will be positively sloped, and the slope of that line will be some positive number. Now let's talk about where the first derivative is going to be negative. So again, the first derivative is going to be negative where the original function is decreasing. So here we can see that we're decreasing from roughly negative 2.5 until negative 1.4. So all right here. And again from 0 to 1.4. So on those intervals, any tangent line we draw is going to have a negative slope. So the first derivative is going to be negative wherever the original function was decreasing. So then finally, we're going to have a 0 slope wherever we change from increasing to decreasing. And we have this horizontal tangent lines. Looks like there's 3 of them here. And so the derivative will equal 0 at x equals negative 1.4, 0, and positive 1.4, because those are the places we are going to have the horizontal tangent lines. Now, these rules that we're working with, they work in both directions. So if for some reason you knew that the first derivative was positive, that would tell you that the original function was increasing. If you knew that the first derivative was negative, that would tell you that the original function was decreasing. And if you knew that the first derivative was 0, that would tell you that the original function had a horizontal tangent line, or that it was constant. So now we want to be able to take a picture of an original function and graph the first derivative. This is not an easy task, and it's something that we need to practice a lot. So here we have an original function. This is where we're going to do our analysis. On the right-hand side, you can see a graph of the first derivative in red, but we have to figure out how we go from the blue graph to the red graph. It's always easiest to start with the zeros of the graph. So to look for places where we should have horizontal tangent lines. So here we're changing from increasing to decreasing in 3 places. So this happens at -1, 0, and 1. So at -1, 0, and 1, the derivative has a value of 0, which means it's going to cross through the x-axis. Now, once we have our zeros in place, we need to look at what the original function is doing in terms of increasing and decreasing to determine if the derivative is going to be positive or negative. So we read graphs from left to right. So for f of x, the first chunk from approximately -2 to -1, this part right here, is decreasing. Since it's decreasing, that means that my derivative function needs to be negative. And that means it needs to be below the x-axis before my 0. So remember, I got to go through 0 here at -1. But before that, I have to be below the x-axis. So since I have to be below the x-axis and I need to go through that 0, I know that I have to be moving in the upward direction. Now, between -1 and 0, we are increasing. So when we're increasing, that means we have to be positive. So my derivative has to be above the x-axis between -1 and 0. Additionally, I know that I have to go through the axis at -1 and again at 0, which means to be above means I'm going to have to turn around to be able to get back to that 0. Now, from 0 to +1, I'm decreasing again. So if I'm decreasing, I'm below the x-axis, and I have to get from 0 to 1, and I have to go back through the 0. So I have to turn around. And then finally, from 1 to 2, I again am increasing. And if I'm increasing, I need to be positive or above the x-axis. So where I have to be is really important. The more we practice this, the better we get at it. Another thing we want to consider as we move along is using some slopes of tangent lines to get more accurate depictions of where our graph should be. So for example, I can see that my graph turns around right here, which looks at like it's approximately 1.5, right? So if I want to approximate where that maximum is, I need to consider what's happening at approximately negative 0.5. So if I go to my original function and I go to negative 0.5, I'd want to approximate the slope of the tangent line at negative 0.5, which is something we were doing earlier today. So I would draw on the tangent line, I'd find 2 points on that tangent line, and I'd approximate the slope of that line. And when I did, I would approximate that it was approximately 1.5. So that's what would tell me how high to go. I could do the same thing by approximating how low I would go between 0 and 1 by approximating the slope of the tangent line at positive 0.5. So here, if I were to draw in that tangent line, I'd pick 2 points on that line, and I would get approximately negative 1.5, which would tell me that my function, my derivative function, would need to go that low. So I can get actual points by using the methods we discussed earlier, but for now I want to get a general sense of above and below, and then we'll refine it a bit as we practice. Example 6. Graph the first derivatives based on the function below. So we're starting with a function that has a u-shape, and we want to get a general sense of what the derivative is going to look like. We're not going to do this precisely and exactly yet. We're going to do this in a general sense. We'll refine it a little bit more once we get to 2.4. We'll refine it a little bit more as we continue to practice. So again, the first thing we want to do is we want to draw in our zeros. So we're looking for horizontal tangent lines. So at x equals 0, we have a horizontal tangent line, which means when we draw our derivative graph, that when x equals 0, the derivative equals 0. Now, from what I learned before, if my function's decreasing, then my derivative should be negative, and if it's increasing, my derivative should be positive. So here, if I read my graph from left to right, it starts off decreasing. So it's moving downward from left to right, which means I need to be negative before my 0. As I move away from 0, I can see my function is increasing, which means that my function needs to be positive as I move away from 0. So now let's think about how this function is going to travel from below the x-axis to above. In order to do that, let's think about what these tangent lines are doing and what they look like. So let's draw in some tangent lines here. Looking at these tangent lines, the slopes are all negative, and those negative slopes are getting less and less steep. So if we were to assign a value to those, they would be getting closer and closer to 0. They would be becoming less and less negative, which means that my function that I'm drawing, my derivative, is increasing. Similarly, when we draw in some tangent lines to the right over here, these values are positive, and they're getting steeper and steeper, which means the y values are getting bigger and bigger. So my derivative has a general function that's going to come up through the 0 in an increasing manner. If I wanted to be more precise about it, I could extend my tangent lines, find 2 points that they cross through, and get the exact number. But for now, I'm still getting comfortable with the general pictures. Let's take a look at another one. This one is similar to the last one. The last one was a U-shape. This one's a hill shape. I want you to take a minute and mentally try to envision what you think the derivative is going to look like based on the fact that the last one was the same exact graph but rotated. What do you think that's going to do to the derivative? So again, we want to start with the zeros. So again, at x equals 0, we have a horizontal tangent line, which means we're going to go through at 0. And then we want to look at what the function is doing from left to right. Our function starts off increasing. If your function's increasing, that tells you that the derivative is positive. And then our function changes at 0 and starts to decrease. If your function's decreasing, that tells you that your derivative has to be negative. Again, considering what the slopes are doing of these tangent lines, we can see that they start off positive but come down towards 0. And then once they reach 0, they become negative and more negative. So we have a decreasing function for our first derivative as we move through our 0. So these two shapes, the U and the hill, comprise most of the functions we look at. There's various U's and hills. So having a basic understanding of what the derivative will look like for these functions will help us build derivatives for more complicated functions as we progress.